Hi everyone, today I'm presenting Mars Modular Agent with Reflective Search from Google Cloud AI Research, published at ICML 2026. The title says it automates AI research. What it really automates is one specific stage of research, and it does not by giving an agent 3 habits that any good researchers already has. The gap between the title and actual scope is the thread I want to pull on today. Here is the plan, why this problem matters, what already exists, and the method, which is 3 mechanisms. Then the experiment, a set of analysis, and I will close with an honest scoping and 4 questions for discussion. Let me start with where the field is. In 2024, Sakana AI released the AI Scientist. The claim is that the entire research loop can be automated. Generate the idea, code, and run the experiment, write the paper, and even review it, end to end for all about $15 a paper. In 2025 came the first proof. A paper generated end-to-end by version 2 passed human peer review at an iClear workshop. At the real first, with a real asterisk, it was a negative research workshop. The paper were withdrawn after acceptance under a protocol agreed in advance, and by Sakana's own admission, none of the 3 submissions met the bar for a main conference. Then this emerged. The framework itself was published in Nature with 2 claims. Their automated review matches human review decisions by their measure better than humans who agree with each other, and one that reviewer grades paper from different foundation models. Quality rises with each model generation. They call this the scaling law of science. So AI doing research now has a manifesto, a proof, and a nature stamp. The question is where this pipeline still breaks, and Sakana names the weak spots themselves: naive ideas, shaky goal, and trouble with complex implementation. To keep the last one in mind. Every system in DISL Lab factors the same 4 stages: idea, experiment, writing, review. The paper puts the bottleneck at stage 2, and the contrast it draws with ordinary software engineering. In normal software, the correctness is binary and a task suite answers in minutes. Here, one check is a training run, hours of GPU. When the score moves, you cannot tell which change moved it, and the code is a repository, not a single script. And this stage gets to everything else. If execution fails, no hypothesis gets verified, and the writing stage has nothing to write about. Here's the number. On 75 real Kaggle competitions, the strongest agent with no medal in 2 out of 3. And then remember what a Kaggle competition is. The problem, the data, and the metric are all handed to you. Agents still lose 2/3 of the time. So the bottleneck is execution, and Mars is a paper about exactly that. Why this stage is so hard? This structure reasons because they map 1-to-1 onto the 3 parts of Mars. First, verification is expensive. 1 checker equals 1 training run. Every experiment regularly costs money. Second, attribution is opaque. Everyone here has lived this. You change the argumentation and the learning rate at the same time. The score went up and you don't know which one did it. This is precisely why we not rerun ablations. Agents face exactly the same problem, and it has a name, credit assignment. Third, the code is repository scale, data loading, model, training loop, evaluation, all interlocking across many files. Existing agent address none of the 3. Mars targets each one directly. Before the method, here is where Mars actually sits. On the ML bench leaderboard as of April, Mars ranks 8 and its scale variant 3rd across those 75 Kaggle competitions, and it currently sits near the top of the ML bench leaderboard. I showed this early so the later numbers have the reference point. This is strong, but it's not a sweep, and a part of our discussion will be what whether the length does and doesn't tell us. So how does this compare to what? So how does this compare to what already exists? 4 lines of work and must take a position against each one. Research automation. There are many AI scientist style systems by now, and they agree on one thing: the execution stage is the bottleneck. Must go straight at it. Existing ML agent, they generate one large single file script. Must moves to a repository level paradigm. Search, grade 3 search, evolutionary, they all optimize performance and ignore compute cost. Where budget awareness exists at all, it's bolted on from outside. Mars bakes the cost into the reward itself. And memory, reflection and its successors summarize logs and record pass or fail. Mars distills a lesson that link a specific code changes to a specific performance change. That difference is the heart of the paper. Concretely, there are 4 baselines, but they share one loop. Generate a script, run it, score it, revise it under gradient or tree search. Their limitations follow. Cost is ignored, so an agent will happily buy a tons of points by turning a 1-hour training run into a 10-hour one, which when practiced is useless. The scripts are monolithic, so they are pressure and can't be tested piece by piece. A memory is a log summary, so the cause of a score change is never identified. Mars is the only system in the table that checks all 3 boxes: modularity, budget awareness, comparative memory. So the method. First, the formulation, because it explains every design choice that follows. The agent gets the task description that makes a dataset and a metric, and it searches over Python programs for solutions that maximize the metric. A crucial part is constraint. The whole search has to finish inside a fixed budget, 24 GPU hours in this experiment. That constraint is what separates this from ordinary code generation. Every candidate rerun is time you can spend on another candidate. So the search isn't just finding the best solution, it's deciding what's worth trying at all. Here's the whole method in one picture. 3 mechanisms, and the easiest way to remember them is as 3 ordinary research habits. Writing clean, modular code becomes a modular decomposition. Keeping a lab notebook, what you tried to and what it did, becomes a comparative or reflective memory. And planning your experiments around GPU budget you actually have becomes budget over tree search. That's the entire paper, and the rest is how each habit is implemented. First, building like an engineering team, not a script generator. The 3 specialized agents run in sequence. An AI ideal agent writes a plan in natural language. A modular agent breaks the plan into independent modules. A coding agent implements each module, unit tests it, and then writes the main script that ties everything together. So what comes out is not one file. It's a small repository. And here's the claim that matters, because it's why this pillar exists at all. Because the code has structure, and edit can be a div. The agent replaces one file or one block, never the whole repo. Because edits are cheap, the search can afford to make many of them. A failure stays inside one module. A module that already works gets reused, and each system only sees the context it needs. The measured effect comes later in the analysis. Roughly for 175 lines in one file becomes 1100 lines across 7 files, and the measure risk goes up. Twice the cost, but extra volume is structure, not a padding. Second, the agent attributes its score change to a specific edit. Follow the diagram. After its completed solution, the new solution is placed next to the current best, and the code difference between them is what gets analyzed. Two agents run in sequence. Empirical analysis reads the execution logs and pull out objective findings, metric trend, sign of overdating. Last distillation takes those findings together with the diff and attributes the score change to a specific edit. The result goes into a curated lesson pool. Each lesson has reports what exactly changed, what the change did to performance, and the general rule to apply next time. One flag now, this is not an ablation, nothing is rerun with the change removed. It's a model reading a diff and explaining the result, and what makes the workable output is that the diff is kept small, because improvements are local edits, and the diff is handed over implicitly. The lesson live here to separate pools. Solution lesson come from comparative analysis I just described. What improved performance debugging lesson come from failed runs, the error, the fix that worked, and how to spot the same problem earlier next time. There is creation. A review agent check every new lesson against the pool and throw out duplicates, and the agent keeps the three most recent lesson in context whenever it improves or debugs. And every applied lesson must be cited by its ID. That's what lessons the author count a lesson uses later and other lessons one by one. Those counts turn out to be the strongest evidence that this pool actually drives search. Third, search within a budget. Every node in this tree is a complete repository with a measured validation score. Blue nodes ran successfully, red nodes failed. There are three ways to expand. First, drop a brand new solution from the root, improve a successful node, or debug a failed one. One iteration is pick a node, create a variant with one of those actions, actually run the code and feed the score back up the tree. In standard Monte Carlo tree search, that middle setup would be a simulated rollout. Here, there is no simulation. The real execution is the evaluation. How does it pick a node? By balancing two pools, branches that have scored well so far against the branches that have rarely been tried. That's the standard city rule. And two limits keep it from getting stuck. A successful node closes after two improvement children, and if the best score stagnates, the root reopens, so the agent starts a genuinely new approach instead of polishing a dead end. Now, the part that makes it budget aware, the reward. The raw metric is a min-max normalized over the nodes seen so far, so scores are comparable across competitors. Then it's scaled down by runtime. The weight is negative, so a shorter runtime inflates the reward. To make it concrete, and this is our own calculation with their weight. At equal accuracy, 4 times faster is roughly 10% more reward. And the weight matters. Their sensitivity analysis show that too harsh a penalty makes a search prefer solutions that are fast because they are trivial, which ends up worse than no penalty at all. One detail that answers an obvious objection. The reward only steers the search. The final submission is chosen by a raw validation score, so the runtime penalty never costs you accuracy on the final answer. One structure point before the result. The core, those three mechanisms is meant to be domain agnostic. Everything that knows about machine learning lives and plugs in. Metadata and data split. Exploratory analysis, a search agent that collects candidate architecture from the web, and a curriculum that goes from simple baselines up to ensembles. The claim is that you swap the plugins and the same core works in another domain. Now the experiments. The setup briefly, the benchmark is MLA bench, 75 rear cat competitions across Fijian, language, and tabular data. The important thing is the controlled comparison. ARDE and ARIA were rerun by the authors under identical conditions. Same language model, same hardware, 1 ABAC, 24 hours per competition. And there is 3 metrics: beating the median human participant, winning any medal, and winning gold. Everything 3 seats means plus or minus standard error. 3 questions. Does it beat the baseline under identical conditions? Does that hold as tasks get harder? And does its sub-3 mechanisms earn its place? First question is that, and this is the head main table. The top block is the leaderboard, and the bottom block is the controlled rerun. Read the last column. Mars win a medal in 56% of competitions against the 38 for AIRA. And the Gordo race 31.1 is the highest number anywhere in this table, leaderboard rows included. But the row I would actually point at is this one. Mars on the older Gemini 2.5 reaches 43%, which beats every baseline running the newer Gemini 3. The scaffolding is worth more than a model generation here. Also, Mars Plus at the bottom is scaled variant to search the trees on 2 backs and 63%. I keep it separate because it's not a like for like comparison. Second question, does the survival task get harder? Broadly, yes. Mars leads on all 3 splits. The gap is widest in the middle, 52.6 against 29.8, about 23 points. On the hardest split, it's 37.8 against 31.1. Absolutely rate for everyone, which is expected, but the margin also narrows to under 7 points, and given the error bars, I wouldn't call that difference solid. What convinces me more on the hard split is this. Mars on the older model matches ARIA on the newer one, exactly 31.1. Same conclusion as before, the scaffolding is doing the work. Third question, evaluations. 4 panels all medal rate over wall clock hours. It's removing one thing. Panel A, modularity. 74 falls to 62 without it. Panel B is the one to dwell on. No memory at all, 51.5. Reflection style look summaries, 62. Comparative memory, 74. So the comparison step is worth about as much as having memory in the first place. That's the strongest evidence in the paper for the credit assignment mechanism. Panel C, search. Credit 59, bilateral search 64, vegetable 74. Panel D, the penalty weight. No penalty gives 64, too much gives 53, the chosen value gives 74. Note that over-penalizing is worse than not penalizing at all. So the takeaway is removing memory costs almost 23 points, the largest single drop of the 4. Same 4 panels on the medium split. Every ordering from the easy split is preserved, and the gaps are roughly double. Memory is the clear least case. 57 with comparative memory against 10 with none. 1 k-bits. This is 10 sample task versus 22 competition on the easy split, so the error bands are wide. And the hardest split, the full method still is every variant, 2 honest caveats. The authors write that the gaps widen on the harder split. That holds against the easy, but not against the medium. The memory gap goes 23, 47, 27, not monotonic. And in panel C, Creedy actually beats budget agnostic tree search here, reversing the earlier ordering. With 10 tasks, I wouldn't overread either of those. but I would rather say them than have one find them. Now, how the system actually behaves. 6 questions. The first 3 check its mechanism from the inside. Then work compliance, then whether the lessons are actually causally correct, and finally cost. If you remember 2 of those, make them the 3rd one and the 5th one. First, what modular decomposition does to the code. 475 lines in one file becomes 1100 lines across 7 files. Twice the code sounds like a regression, so let me say what it isn't. The extra volume is structure, configuration, data loading, model, training group, and utility each become a unit that can be tested on its own and patched by dev. That's what makes the debugging loop cheap. The lower table is the part I like. The module layouts are designed per competition, not from a template. Image task get a dataset, an engine, a model, while the fashion recommendation task gets an embedder, a retriever module, and a ranker, which is the standard two-stage recommender design. Nobody told it that. Second is the budget-aware search actually explore better. The measure is expected solution rate. Of all the nodes exploded, what friction improved on the running best? Budget awareness lifts it from 16 to 19.5%. Fewer wasted expansion. The scatter plot shows the mechanism. Look at the vertical line of points near 98% accuracy. The same score is reachable in 1500 seconds or in 10,000. Without a runtime term, the search treats those as equivalent and may well chase the flow one. That's the whole argument for the cost term. Not that speed is good in itself, but the time saved is the search you get to do. Third, showcase research, one hard fine-grained image competition, and the entire search tree. 4 ideas are derived from the root, and every node is labeled with the lesson it applied. Follow the score, 0.46 for the first lightweight network, after the threshold tuning and the learning rate schedule, 0.62 once the backbone is upgraded, and 0.66 at the end, which is the silver medal. Now look at the red node. The ensemble ID starts as a failure. The agent distills a lesson from that failure, applies it together with an earlier scheduling lesson, and the very next node is the best solution in the whole tree. That's what the authors call the aha moment. The number to keep is 63%. Most applied lessons came from a different branch than the one big work on. That's the argument that this memory generalizes rather than memorizing one path. Hold on to it because it cuts the other way in 2 slides. First, work compliance. The authors report the zero violation across everything monitored. No unauthorized resource access, no external API calls, no handwritten submissions. The histogram is a plagiarism check against the top public hacker notebooks. Maximum similarity stays under 0.42 for every submission, well below the 0.6 threshold, and the distribution overlaps that of the baseline. The meta therefore do not come from copied code. One limitation, the test measures token level similarity. If the agent retrieves a description of the winning approach and re-implements it independently, the resulting code is dissimilar and the check passes. Strategy level contamination is not evaluated, and this applies to every system on this benchmark, not to Mars alone. Fifth, the paper answer to the credit assignment question. Be precise about what it establishes. An LLM audited all 3,600 lessons and judges 88% to attribute the matrix if to the correct code change. Training were then verified by hand at 90%. The audit, however, tests whether the explanation is consistent with the code diff and the logs. Nothing is rerun with the change removed. Consistency is necessary for culture correctness but not sufficient. So 88% is an upper bound rather than a measurement. The second example on the slide shows what a sound lesson looked like. An ensemble underperformed its own best single member because one backbone had converged faster and the agent distilled a negative constraint from that failure. Roughly one lesson in 8 is therefore misattributed, and the 63% crossband transfer is the mechanism that spreads it. The last one is KAIST. This theory is the Gemini 2.5 run, so the meta rates read 43 and 24 rather than the headline numbers. At 24 hours, Mars costs $60 per competition against the 39 for ARIA and 11 for AIDE. The driver is context. Every core carries the lesson pool and the module sources, which more than double the input tokens. The 40-hour column is the answer. It spends $9.60 less than AIDE over a full 24 hours and still reaches 28% any medal against their 24 and 23. A better research on a smaller budget, so the gain is not purchased compute. Let me wrap up. 4 takeaways. 1. The reframing. Previous agent treat this as a writing a script. Mars treats it as a searching for a repository under a computer budget, and the reframing is what makes everything as necessary. 2. The mechanism, modular construction, so the code is testable and editable. Comparative memories of failure become reusable knowledge, and a reward that prices runtime. 3. The numbers, open source state-of-the-art under controlled conditions, and the highest gold rate anyone has reported. 4. It's reproducible. Code prompts and full trajectories are released, and the authors themselves name inference costs and lesson reliability as the open problems. Back to where we started, with honest scope. The title says automated AI research, but what's automated is execution stage, choosing the problem, forming the hypothesis, judging whether a result is interesting. None of that is here. And even the execution is a Kaggle proxy, where the problem, the data, and the metric all arrive pre-specified. Real experiments have none of those given. To be fair, the authors never overclaim. The paper positions itself as reserving a bottleneck, not a full automation. So what survives deflation? The finding that habit beats brains. Budget awareness, modular construction, and learning by comparison are ordinary researcher habits, and transplanting them into an agent bot more than a model generation did. That stands regardless of what we call the task. And if you remember one line, good engineering habits transplanted into an agent are worth more than a model generation. The evidence is the row we saw twice. Mars on the older model beating every baseline on the newer one. 3 habits, 1 per mechanism. Write modular code, keep a lab notebook, watch a budget. And the authors are candid about what's unfinished. The other domains, the cost and the reliability of the lesson themselves. So this is the end of the presentation. Thank you for listening and attending today's reading group. If you have any question, feel free to ask.